Good evening, everybody, and welcome to Astronomy on Tap Atlanta. In our brand new location to try to avoid the rain that will never come tonight. It is my pleasure to introduce the first graduate student to be awarded a dual PhD, Dr. Fallon Konow. Fallon is the first person to receive a dual PhD from Georgia State University and the University of Rome Sapienza. She specializes in creating instrumentation to small telescopes to observe the sun in multiple locations across the Earth, which means with that array you can observe the sun for as long as possible, regardless of where it happens to be setting. And Fallon has worked with me for many, many years because she was one of the founding members and one of the graduate lead ambassadors for the Georgia Outreach Team for Space, and she was a part of us when we first launched Astronomy on Tap Atlanta almost 3 years ago. So, without further ado, please keep it going for Dr. Konow.
Thank you, Justin. Hi, everybody. Can everyone hear me okay? I was told the microphone is temperamental. So I'm here to talk to you today about the tools of the trade from screws to solar science. So how do we build a telescope? I'm sure all of you have been wondering this whole time, all the Astro on Tap talks. How did we get there? So there are many different steps to build a telescope. First, you need to decide your science. What is it that you're actually trying to target and observe? What type of light are we looking in? You need to decide your budget. The telescopes I'm working in are cost effective. That means they're cheap. And then you need to obtain the parts and build the telescopes and finally observe. And so there's a lot of different steps that I have broken down here, and this seems pretty straightforward. It's only 6 steps, but this is what it actually ends up looking like. You're trying to decide your science, and then you apply for money, but you don't get the money. So you have to apply again, and then you cry, and then you apply again, and you keep applying, and eventually you'll receive funding. You might need to change your science a couple times, but you'll get there. And then, okay, we did the hard part, right? No, we have to wait a lot to determine the parts we need. You have to wait on the shipping, find the parts that are from university-approved sellers because some other sellers you can't buy them from. And then you need to order less parts because you don't have the money. And then you order the parts, and then you wait and wait because they get stuck in customs. And then you figure out you needed more parts, and you have to start again, and then apply for more money. And okay, that must be the hard part, right? Then we just build a telescope? No, then we have everything go wrong, and I'm going to blame the elves. So in the lab, you have to align optics, you need to do all of the electronics, and then you'll do this all one day, and the next day, it'll be broken. So I blame the elves. And then finally, we did all the hard stuff right, and you can just observe your target? No, because sometimes it's cloudy, sometimes there are fires in California, and sometimes it's cloudy in California, but sunny in Rome, so you can't observe at the same time. And then finally, you can observe, and the telescope didn't work. So basically, how to build a telescope, how to get all this lovely data you've seen before is a constant loop. So let's start from the top. And also, sorry, Murphy's Law is going to be a big thing here, which is everything that can go wrong will go wrong. This is something to remember, and also if you want to blame anyone, blame the elves. It's just the easiest. So let's start with the top question, deciding the science. This is going to be the longest part of my talk, and it's actually the longest part of this project as well. So we're starting off, what is our target? My target is the sun. So just a little background of what is the sun. The sun is our star at the center of our solar system. I want to highlight it is a 3-dimensional object. This might seem like a trivial statement, but it is not, because a lot of times when we're observing astronomical objects, we just see points. So it's a 2D or a 1D thing. Our sun, we can see multiple layers in its atmosphere. And something that's really interesting about the solar atmosphere is plotted over here. This is showing the temperature of the atmosphere versus the height above the photosphere, or the base of the atmosphere. And as you can see, we have a pretty steady temperature that then increases as we get higher, which is very weird. If you think about the temperature in the atmosphere on Earth, as we go up, things get colder. So this is one of our science targets, trying to figure out why does the atmosphere of the sun get hotter? Another thing that we're trying to understand with the sun is called space weather. So what is space weather? Space weather is an eruptive event happening on the sun that then affects us here on Earth. And so space weather events are things like flares, coronal mass ejections, solar energetic particle events, basically high energy eruptive events that release particles and send them to Earth. And they have effects here on Earth, some that can be very positive and pretty, like our aurora, those are all due to space weather, but some that can be really detrimental. Like they can negatively impact our communications, they can down satellites and degrade power grids. One of our biggest flares that have happened in the past couple centuries, down the entire northeastern seaboard's power lines. So this is something that, and especially in our increasingly digital world, we want to be able to understand what's causing these events, predict them, and therefore prevent these negative outcomes. So those are our drivers for what are we trying to observe. Now, if we want to be able to observe the sun and understand what's causing its heating, what's causing these space weather events, we need to know what type of data do we need to take. And these are the data that I take. They're called magnetograms, Dopplergrams, and intensitygrams. And I'm going to go through each of them, but I'm actually going to go backwards because intensitygram is the simplest. It's simply all of the intensity of the sun's light in a particular wavelength. A Dopplergram, this is line of sight, shows Doppler velocity. You can think of blue as coming towards you and red as going away from you. As we see here, the rotation of the sun. The sun rotates just like Earth, a little bit different, but we can think of it as just a current rotation. And this white line shows a zero velocity line. So here we see the sun rotating towards and away from us. And from using a Dopplergram, we can determine things like wave properties that are going through the atmosphere. And then moving all the way to your guys' left, we have a line of sight magnetogram, which is the magnetic field lines on the sun. So the black and white you see kind of looks like a cookie, is showing the positive and negative magnetic field lines. More magnetic fields, more complex, means more active and more likely to have these eruptive events. And so there are interesting things we can learn from each of these data products. Great, we want these data products to do our science. How do we actually build these data products? We take something called filtergrams. So this is an image from the sun, again from my telescope, that are in different polarization states of light. So what you're seeing here are 4 images of the sun in slightly different wavelengths, red and blue wings, of right and left-hand circular polarization. I'm sure all of you are really familiar with polarization, but in case you're not, we have a quick aside to talk about polarization. I happen to love polarization. Most people do not. So light propagates along particular planes of existence. So imagine light as a wave. It can propagate linearly towards you in vertical or horizontal polarization. Think of it as things like how a dolphin swims or how a fish swims. It's still coming at you directly, but it's 2 different states. Light can also propagate in circular polarization, which does not have fun animal correspondings, but right hand or left hand circular polarization. Another thing that's very exciting for me and important about these polarization states is that you can add together the linear polarization to get a circular, or add the circulars to get a linear. And so my telescopes are going to leverage these properties in order to go back and see these filtergrams again and image the sun in our different polarization states. So what's important about imaging these polarization states is that they're sensitive to different types of the magnetic field. So we're able to actually produce those magnetograms and Dopplergrams by getting the different wings. Great, we want to get filtergrams. I need to take a step even below that. What type of instrument are we going to use to do that? We're going to use a magneto-optical filter, an MOF or a MOF. I will use them interchangeably throughout this talk. I'll try to stick with MOF, but I apologize if I use MOF instead. What this instrument physically is a glass cell with an ion of choice. In the case of my telescopes, potassium, sodium, or helium, that's placed in a magnetic field. So what you see here is our glass cell and our magnetic field that's going through the cell. It's along this dotted line. And this is what's going to produce our physical effects that allow us to image Doppler and magnetograms from those filtergrams. What the telescope actually looks like is something like this. There's a lot of images on this screen. These are my 2 different telescopes in the network. Sadly, we're going to ignore the bottom one for now. Forget Rome exists. This is the telescope scheme out in California. There's still a lot going on there, so let's look just at the first part. This is the setup of our magneto-optical filter, and it looks physically something like this. We have our glass cell inside of our magnets placed between 2 crossed polarizers, P1 and P2. So these polarizers only allow a specific type of polarization through. Remember what I was showing before, dolphin or fish? Our first one only allows dolphin swimming through. And our second one is crossed at 90 degrees, so it should only allow fish swimming through. And you would say, Fallon, that means no light would get through. And you would be right. That is what we're leveraging with this instrument. By putting our cell inside a magnetic field and getting the presence of vapor, we're having two physical effects happen that allow our dolphin swimming light to change into fish swimming light. These are called the inverse Zeeman effect and the Macaluso-Corvino or Faraday effect. I apologize they're at the bottom. I thought using some fun vocab words would be nice. But what these effects physically are is the inverse Zeeman effect takes the wavelength of light we're looking at, let's say potassium, and puts the red and the blue wings out from each other. It separates them apart and puts them into emission rather than absorption. So what it means is that we can see red and blue wings of this line. And then what the Faraday effect does is it changes the polarization state. So what we end up with through that next polarizer is just a red and a blue wing of our polarization state of choice. Now, I covered half of our instrument, so what we have at this point are two wings, red and blue. Using the second half of our optical scheme, we're able to select just one, so just one of the filtergrams, red in a polarization, blue in a polarization, red in the other, blue in the other. And what we end up with are those lovely filtergrams. So every time I get an image, I'm actually getting 4. If you look at these, you might say these look almost identical, but I encourage you to try to see a slight brightness difference. If we're looking at the positive on the red, it's brighter on the bottom and then brighter on the top. And that's what we're looking at when we add them together, we get those Doppler and magneto effects. So we have decided what our science is. We are going to target the sun. We're going to observe in potassium, sodium, and helium in magnetic field and line of sight velocity. Now let's apply for funding. There are many different types of funding you can apply for. I'm going to highlight funding that funded me and my instrument throughout this project because they put in a lot of work for me to be here tonight. One type of funding is from universities. So I've been really lucky to work with 2 different universities, Georgia State here in Italy, here in the United States, and the University of Rome out in Italy. So I have 2 different universities funding me for my personal scholarship. And then actually the most expensive thing about instruments, especially cost-effective instruments, is the people working on them. So I have my stipend that has been funded, and also different internships that have funded parts for our telescope. So in addition to university funding, you can have grant funding. So I've also been funded by NASA. NASA has funded a lot of my travel, my stipend, a lot of parts for the telescope, and also specifically the Georgia Space Grant Consortium, which is what has been running Astro on Tap and it got space, funded my internship out at JPL that worked on the filter. So you can have government funding and national funding like this. I've also had NSF fund me to work on some travel and some workshops. So I worked with the SHINE workshop, which is a workshop for solar, heliospheric, and interplanetary science. And so you can have university funding, government funding. You can also have private funding. Our telescope, specifically out in California, is a collaboration with the Eddy Company. And so they funded quite a few of our telescope parts, a lot of my work out there in general, giving us observatory time, and just being overall a help and a collaborator on this project. So funding, like I said on the original slide, takes a long time. This has been a lot of different applications. A lot of this funding happened before I even joined the project 6 years ago. So I know this was a short slide, but just think in your mind, we sit in the funding phase for a very long time. Once we have funding, we now need to order our parts. We need to determine what sort of specifications that we actually need. For example, with the sun, we have a lot of light coming in on specific optics. And so we need to have things that are heat sensitive and can block certain amounts of heat and can take certain amounts of heat because we are focusing all of our light to a certain point. Remember when you were little and you had a magnifying glass and you held it up to the sun and you tried to set bugs on fire? That's happening. If I put my hand in my optical scheme, it actually burns. So we need to make sure all of our optics are able to handle that much heat. So where do we buy our parts? One of our favorite places, and by our, I mean every astronomer is clearly, I'm sure they know this, is Thorlabs. Thorlabs is basically our go-to for anything optical or mechanical. So it's where we buy things like our bases for all of our optics, the rails that make up our telescope, a lot of our filters and lenses, and also anything that is used in the lab itself. We're also partial to Thorlabs because with every order you buy, they send you a box of snacks. And I can say the snacks coming in Europe, because they come from Germany, not as good as the US ones. When we need specialized optics, there's a couple other places we buy from, places like Edmund Optics or Luxa, or if you're lucky enough, like we are, to work with a company that does optical coatings like Edico, you do specialized optics there. A lot of times, like I mentioned with the heat sensitivity, we need specific transmissions on our optics as well, so we have very specialized optics that only allow specific wavelengths or polarization states through. In addition to having to buy a lot of things, if you're lucky enough to work with machine shops like we are, you might personally make some of our stuff. So all of our optical, our MOF equipment with our magnetic assemblies are made at the Edico, which is our private collaborator out in California. And then both here at Georgia State and in Rome at Sapienza, we have a machine shop that allows us to design certain parts and build things ourselves. So what you see down here is a designed, built in our machine shop, actually at Tor Vergata, another university in Rome, holder for our camera. That's in conjunction with a couple different Thorlabs optics and then a camera from another site. So we're doing a lot of Frankensteining to get our instrument built. Great, we have all of our parts. What do we do now? We have to run tests and align optics, and we are afraid because this is where all of our elves show up. So the first step in building a telescope is introducing you to what my telescope parts actually are. So in building the telescope, I want to introduce you to our Gates network. This is the telescope I've been working on for the past 6 years. It consists of 2 current channels. The Mojave Solar Observatory is out in California, in Apple Valley. It's about 90 minutes northwest of LA, so just think, go over the mountain, drive into the desert, keep driving, question why you're living there. That's where the telescope is. And then out in Rome. So this is the Tor Vergata Solar Synoptic Telescope. It's currently located at this yellow dot, which represents our academic institutions, so University of Rome, Tor Vergata, and Georgia State, but its final mounting location will be in the Canary Islands of La Palma, Spain. So these are my 2 telescopes. I love them dearly. I'm going to introduce each of them in a little bit more detail. The first one being the TSST. This is my telescope out in Rome. It actually consists of 2 telescopes, a magneto-optical filter, MOF-based instrument that you see up at the top, and then an H-alpha commercially available telescope that you see at the bottom. I spend most of my time on the MOF, so we're going to focus on that. And what you see when you look at this telescope might be a bit of a weird shape, because I remember vividly being asked this question at my prospectus talk, Fallon, why is your telescope a box? I thought telescopes were round, like that H-alpha one at the bottom. And my telescope is round, it's just much smaller than you might be thinking. This optic you see right here is our round entrance, and it's about 2.5 inches big. And so we just have smaller entrances than most telescopes tend to have. And that's because we're looking at a very large, very close, very bright object, so we're able to have smaller objective lenses. So the telescope you see up at the top, light comes in from the bottom left, bounces up to the top, and then goes along the top rail. And this is the type of telescope where we're getting those 4 filtergrams of different polarizations of light. Then we have MSO, our telescope out in California. It's very similar to this telescope in Rome, although it has 2 channels of magneto-optical filters. So rather than coming in the bottom and going up the top, light comes in the front of this rail, all the way on the end, and then splits into 2 different channels. So we can observe 2 wavelengths, sodium and potassium, or helium and potassium, at the same time, and that corresponds to 2 different heights in the solar atmosphere. So with our telescopes, we're able to observe multiple heights from multiple locations on Earth in magnetics and velocity. It's pretty exciting, but we need to build it. What is the first thing we need to do? We need to align all of our optics. And I have a nice little schematic over here on the right to show you all the different types of alignment we do. So firstly, we have the x-axis, moving it sideways, the y-axis, moving it up and down, the z-axis, moving it along the rail. But then we also have rotating it, tilting it, and then also making sure everything is just perfectly flat in its casing. So there's 2 different steps to aligning each optic. The first step is to align each individual optic, and this highlights the tip and tilt and the rotation. I don't know if you can see the little green dot on the pictures over there, but the way we do this is we set up a laser and a mirror. And so we put the laser through our optic, it bounces off a mirror, comes back through the optic, and hits the target. And I do this for every single one of those optics you saw on that telescope. If you didn't count, there are 27. And so you do this for each optic, and then we put each optic into the telescope in order. So that is moving along the rail, and we can then fix the height as well as the position on our rail. And so for this one, we again use a laser and a target. You're seeing that little green dot. There's a lot of them. That means something's misaligned. I need to fix it. In Rome, we just use a red laser. It's the same idea. But we also get to use some fun instruments. This is called a shear plate, and it tells us if our optic is in the correct position. All of these little lines you see should be parallel. If they're not, look at all wonky. But unfortunately, I did not take pictures of bad alignment. This was my proof to my advisor that our optics are good. So once we align our optics, we leave home for the day, we come back in the next day, and the elves have changed everything, and you need to align the whole telescope again. I have aligned each of the telescopes I introduced you to, I think 4 times individually. And most recently, out in Rome, we've redone all of our optics for a 5th. So it's a lot of redoing things, and that's simply because they're very sensitive. Any little touch can misalign them. Anything that applies heat or pressure will just change things ever so slightly, and we want to make sure we're as focused, as aligned as possible. So we've done all of our alignment, and now we have lab tests to run. Before we can observe on sky, there's a lot of things we need to make sure that are working other than our optics. We have to make sure things like our cables are set up and that our power supplies are working properly. We have to have all of our circuits working. You have to make sure they're wired in properly. I did accidentally explode this specific circuit you're looking at last week. We had a backup, but that's not always the case. If we don't have a backup, we need to go back to order more parts and get more funding and wait for customs. We have to work on different tests that we build, and sometimes our building tests are a little bit, I don't want to call them janky, but this is in fact a piece of plastic taped over our camera to make sure that no light is coming in. And so we get very creative in our solutions. Other tests, like things like fixing our cell had leaked potassium, and we needed to rewire the whole heating, melt potassium with a soldering iron to put it back in its well, and then hope for the best that it actually still worked. We do other things like making sure our observational schemes are set up. We heat all of our cells, and so our heaters need to be working, holding to a particular temperature within a certain temperature degree. And so there's a lot of different schematics that need to be set up in order for us to observe, even just for one image. Then we also have more creative solutions. This is bubble wrap over our observatory hole, which lets the sun into our telescope. And this was an attempt to create flat images to test, are we getting any aberrations from our camera? And then our final image I want to highlight of our creative solutions are sometimes you just need to hide under an umbrella because we're doing cost-effective observing here, which means we don't always have fancy domes and fancy telescope setups. So we need to make sure all of our optics stay cool enough that they can run. So we run a lot of lab tests. And of course, the elves mess up a lot of them too. So sometimes you'll get the temperature control working, and the next day it just simply won't, and we don't know why. And so a lot of times all of these tests need to be run and rerun. But finally, we get to observe. And there's a lot of things still that go into observing, like figuring out what day we can actually observe. With 2 telescopes, it's things like, can we observe today? I don't know, is the sun up in both locations? How's the weather? Right now here it's pretty bad, but it might be okay in an hour. How is the telescope actually working? Did the elves break things? In the elves' defense, these 2 pictures were both my fault. Sometimes the cells break if they're heated too much. This image you see here of the crazy optics, we did not have a proper filter on, so we were getting too much light. And you see that black line on the top. If you don't use the proper cables, they will get too little power, and they will not be able to transmit our image across 2 meters, which is the distance from our actual telescope to the computer. So these are things that we don't necessarily know until we go to observe, and we need to do them again. And then finally, you have to fight Murphy's Law. So the image you see up at the top, our observing was supposed to start in January of 2025. The entire state of California was on fire, and so I was unable to do that. Also, if you have been paying good attention, you'll notice I have one telescope that's here in the US and one that's here in Europe, and they use different units of measure. And we have, in fact, had issues that we have been trying to send data between two locations. One is designed in imperial and one is designed in metric. And that was a problem. Once we fixed all of this, we finally get to observe. Look at the sun, isn't it pretty? Fallon, that's not the sun. These are calibration images. And so these are things that we need to take on top of our intensity images of the sun. The first one is called a dark frame, and this is used to determine how much noise we're getting just from the heat of the camera and the telescope, because that might show up as an observation, but it's really just noise. The master flat is called a flat because it's supposed to be a fully flat illuminated image, and this is used to correct for aberrations in the optical path. So think of if there's a piece of dust on one of the lenses, you might think that's a thing on the sun, but actually it's not. So this flat will pick that up and correct for it. And then my telescope has something called leak through, which is an image with the polarizers to see how much light is just coming through them. Once we get all of these calibration images, we then need to know how are we going to calibrate our data and return those pretty Doppler magnetograms. This is a very complicated graphic that just shows you all of the steps that we needed to code up to see how it's going to work. And so what it means is we take all of our baseline data, those calibration images, and oh look, that is actually a picture of the sun. So those are our filtergrams. And we apply our calibrations and get raw calibrated filtergrams. But we need to apply some different techniques in order to turn them into Doppler and magnetograms. So once we get filtergrams, we need to add them together in different ways to get what's called level 2 data. But if you're looking at these, you might notice specifically up top, we have some weird halos going on. And that's because these are misaligned. When we're having 4 different images of the sun, we need to make sure they're perfectly aligned so that way all of the features line up and we don't get superfluous observations from them being misaligned. And I personally would like to blame the elves for this, because these 2 images you see at the top and bottom went through the same exact data reduction pipeline that I created. And you'll notice down at the bottom, there's significantly less halo than up at the top. I still have yet to figure out why this is. I'm working on it, but let's just say I fixed it. Everything's working fine. Once we get from here, we then go to our level 3 data, which is not only properly aligned all of the disks, but corrects for, oh, we're not observing the sun in north-south, we're observing it on its side. So we rotate it correctly, we mask out the back because we don't care about the back. These ones specifically are summed to a different observation time so we can better analyze them. And we have these lovely pretty data that I can give to all of our observational astronomers as opposed to the instrumentalists. But this is just an example of 1 day of data. People usually want more than that. So finally, we have an observing campaign. I was lucky enough last summer to go on an extended observing campaign that consisted of 3 parts. Our first phase was a dual site observation, so using both Rome and California at the same time. We observed for 9 hours with both telescopes so we could show we can do science with 2. This last data point is saying that how much of active sun and space weather events we actually caught. So we caught 5 C-class flares, which are medium intensity notable flares. Then we had an extended observing run, which is phase 2. And this was just California. This was me every morning for 378 hours over the course of 45 days, waking up an hour before sunrise to go get 2 heights of observations so we can look at waves throughout the atmosphere. We averaged about 8.5 hours per day, and also we saw 83 C-class and 6 M-class flares, M being stronger than C. So with these data sets, we're getting a lot of good space weather data, which I'll remind you was one of our science drivers. And then finally, the final phase was the helium phase. I worked on a different instrument developing a helium filter. I'm just going to mention it and point it out there, but I can go into hours of helium talk because helium is my favorite. But we were able to catch a couple more flares with helium, and we got about 30 hours of helium observations. We built a telescope. We did it. We have data. But if you don't mind, because I was told I had 5 more minutes, there's one more step beyond that, which is data analytics. And I spent the last 6 years building a telescope, so let's actually look at some of the data we can get from this solar telescope. Let's go and look at our Dopplergrams. The ones up top are the ones I showed you before. So line of sight, rotation of the sun. Blue is coming towards you, red is coming away. They should look like the MSO ones with a vertical white line, but you'll notice all the way on the right, which is TSST, our lovely Roman telescope, has a bit of a weird squiggle. That is not the sun. That is instrumental effects from how we're taking the data. We have something called fringing and something called vignetting, which means we're blocking some of our light, and we have internal reflections in our telescope. So we're looking to correct for that, but at the bottom, you'll see all three of these look pretty similar. They were moving like a video, so let me see if I can get them to start again. These are what are called rotation subtracted Dopplograms. So if we subtract off the rotation of the sun, what we're left with are these granular patterns called supergranules, which are convection patterns in the sun and allow us to investigate things like flows going up through the atmosphere, particularly if we stack them like this. That was one of the science targets of our extended observing campaign with MSO in California, using 2 different heights in the atmosphere to observe waves going through the atmosphere. So let's zoom in on waves through the atmosphere. We can look at something called a power spectrum. This is a one-dimensional power spectrum. Our y-axis is showing the power of a wave, and our x-axis is showing the frequency. So frequency just being 1 over time, basically the period of these waves. And you'll notice they all peak around the same point, 3.1 millihertz, which is a very special frequency in the sun. This is the frequency of a P-mode wave, or a pressure mode, which is a very typical wave that propagates in the solar atmosphere. The 3 colors you see are the sodium channel in green, the potassium channel in orange, and then the cross spectrum, which is some fun math of the sodium and potassium channels. One thing I want to highlight in this 1D spectrum is sodium is higher in power than potassium. Sodium is also higher in the atmosphere. This is something we expected to see, but it is very encouraging that we see this, that waves' power is increased higher in the atmosphere. If we look at 1D spectrum in 2 dimensions, we have a very complex plot here, but I think it's really fun to look at. So I'm going to take the rest of my time to explain this plot to you. What we're seeing is frequency on the y-axis, and then horizontal wave number on the x. That's a very fancy way to just kind of say position. It's an inverse position in Fourier space, but position. The lines you see, there's a black line, a cyan line, and then a black and cyan dotted line. Our black line is called the acoustic cutoff frequency. It's at 5.6 millihertz, and above this black line, we don't expect any waves to propagate in the solar atmosphere. So we just expect this to all be noise. I think this is pretty much noise. This cyan curve is the curve of what's known as the F mode, or fundamental frequency. So this line should trace the fundamental frequency lines of waves in the atmosphere. What we should see above this line are kind of finger-like fans that have the same shape. And I don't know if the contrast on the screen is looking great, but we see that. We see these finger-like fans. And then this dotted line is what's called the acoustic gravity cutoff line. And so below this line, if we saw acoustic gravity waves propagating, we would see something going on down here. We don't expect to see this at the wavelengths I'm looking at, and we don't see it. We just see some noise. So the line that we care about the most is this cyan line, and we see these finger waves going across. Our color is power. So rather than in 1D when we had on the y-axis power, the color is now power. So brighter colors are more power. And we can see that we see this finger-like fan. And this might not be that exciting, it's not that intense, but this shows that my telescopes can be used for wave dynamics. Really exciting, our cost-effective telescopes can do science that is really exciting and helps us understand things like the heating of the solar atmosphere, or understanding what's happening before a space weather event like a flare. So if you want to hear any more about these lovely plots, I'm happy to talk about them. They're one of my favorite things. But I was here to talk to you about how to build a telescope. So we'll go back to, we did it. We turned screws into solar science. We went through all of these things, waded through all of the timelines, actually got some data analytics done, and we did not let the elves win, which is always a great thing. So with that, I'm going to leave you with, if you want any more information about Astronomy on Tap, we have our website and our Instagram. And if you would like to leave a tip, we also have a QR code for that. And I think I'm going to give it back to Justin before I take any questions. Thank you.
That's what happens when you book a professional. Everything that I was just about to say, she already said it. So, any questions for Dr. Fallon?
Hi, Fallon. That was a fantastic talk. I'm wondering if you can talk a little bit about the logistics of now transporting your Rome telescope to the Canary Islands, and if like you have a location there with a dome, and also if there are going to be any problems with realigning the telescope, if there's going to be any issues with transportation and things like that.
That is a fantastic question that I don't have pictures for right now, but in my defense, I had backup slides for. So we'll just go back to my map because I actually do have the picture of our dome model there. So the basic answer to your question is there's a lot of considerations, including things like customs. But keep going, we're almost there. First answer, the dome. We are working with a industry collaborator out in Rome that is ADS International. I do not remember what those letters stand for, but they are designing our dome for us, including the mount. So the mount is the bigger thing because it has to have specifications for how to point, how specific to point, and also we're looking for all these telescopes to be automatic. So our dome has to be able to close automatically in wind and weather, and they're doing all of that for us. We've done all of the specifications, and we just give it to them. So that's really nice. The bigger issue you'll notice is our distance here, transporting our telescope. I will point out these are not horrendously big. They're about 2 meters long, 6 feet. I can hold them, but I can't hold them by myself because they're kind of heavy. So as far as shipping costs go, not that difficult. They will fit on a standard train, car, boat, plane. But it is, yeah, just any of them. But it is the realignment. So we will do a full alignment here. We will hopefully say it won't be changing alignment. We will get there and then we will do fine alignments. We won't do all the optics again, but what we'll do is probably just test individual optics rotationally. And I think that was it. Yeah. So there are a lot of considerations, but we're getting there.
Have you seen any specific flare precursors, and in which wavelengths has it been?
That's a fantastic question. So the precursor I was looking at specifically has to do with the Dopplergrams. So let me go all the way back to power and stuff. We'll get there. There's a lot of elves. Yeah. So I'm looking specifically at precursors and Dopplergrams. In magnetograms, they're used very frequently for like how complex the cookie is, and they're fed into AI models. I don't touch AI at all, but I hear they're really great. I'm looking specifically at these fingers here. This is power. You can also make this plot with phase. Phase being the difference in travel time between the two heights. So the first question was the wavelengths. I'm looking at potassium D2, which is 589 nanometers, and sodium D2, 589, and potassium 1, which is 770. So they're both in the optical, and they correspond to the photosphere, so the base of the solar atmosphere, and then the low chromosphere, so about 500 kilometers difference in the atmosphere. And what we've seen previously is that the phase or the travel time between these two heights prior to a flare drops. And so we can see that, again, I don't have the plot up, but imagine this rather than power is travel time. It looks almost identical. And so looking at a quiet sun, we would see, oh, the travel time fingers are very normal. They show that it is 500 kilometers between them. And then in a flaring region, it shows negative time or no time. And so this is something that we're investigating. We just don't have a statistically significant sample yet. So we need more data to see if this actually works.
Any other questions for Fallon?
I have a very simple question. Why is there more orange on the left side of the plot? Why do you get systematically higher power towards lower wave numbers?
Yeah. A couple things. One could just be noise. Our wave number, the resolution of it, you can almost see boxes if you look really close. That has to do with our resolution of the telescope. If we had a bigger telescope, better resolution, these would blend together less. So some of the brightness is just that these fingers are blending together. Some of it is also that there is just more power observable at lower wave numbers. So lower wave numbers being like longer wavelengths, and so they're easier to observe. And there's also just more of them that are in the atmosphere as opposed to these. Like if I could extend this out, it's just all blue. So blending, need a bigger telescope, and then also just systematically of the sun, what's there.
Any last questions? Alrighty. We will be sticking around for a moment. Unfortunately, that won't include observing, but if you have further questions for Fallon or for any of us scientists, please pull us aside. But in the meantime, let's give Dr. Fallon one more round of applause.